record our session and share. You can share your screen. Please, you have a word.
Hello, I present our work, Lytvyn again for semantically robust unpaired image translation. Let's start from problem setting. Suppose we have two data sets of images. First, it is European city image, cityscapes. Another data set is images from GTA 5 video game, synthetic images. Image translation is to make input image from video game to look like it is image from European city. Something must be changed. For example, yellow city lane of American cities should be changed to white lane line. How to do translation? Let's look at GAN architecture, generator and discriminator. Input image after generator becomes some synthetic image, fake image. Generator may be UNet architecture or other, but it makes first our net generator makes from input image generated image. Other network discriminator classifies is it real or fake image. So generator and discriminator compete together. One wants to make image such that it is indistinguishable from real images, but another discriminator tries to discriminate which is real, which is fake. In such setup, we can achieve that generated images are very close looking to real images from other image domain. But there is nothing to ensure that translated image have features from original images. It could be can learn such one image that is it is looks like European cities and will output it for any input image. That is bad. So our second problem is that generated image reflects individuality of input images. How to do that? One of approach is travel GAN. Authors propose to add Siamese network which translates image into some vector in some hidden space. Image embed. And after that, we can use linear algebra, like in neural language processing, word2vec, for example, where a batch of input images have the same distance among themselves as a batch of resulting output images. What does it mean? Input images have an input image connected with output image with some rule. And this rule can be learned by a Siamese network. So differences from input batch and difference from output batch must be the same, and the difference is travel loss that together with adversarial loss from discriminator can be used for training all that big network from 3 networks. And total loss of generator is adversarial loss plus travel loss multiplied by some coefficient lambda, weight of travel loss against adversarial loss. I tried to learn to teach such network, to explore it, but we should change dimensionality of a vector. We should choose. We should choose architecture of some Siamese network, train parameters, and the lambda coefficient. I believe that it is impossible to find optimal parameters as they are so much in such a complex network where generator, discriminator compete. What is our intuition? Half year ago, Kaggle competition Google image embedding had the purpose to embed any image into 64-dimensional vector. In top of leaderboard, all decisions were they used clip network. It was superior over all other methods. What is clip network? It is two encoders, text encoder and image encoder, that are learned together, trained together to encode text and image that are connected. Text is a caption of image into some hidden space. That is the same idea that Siamese network between input images and output images. They should encode it into some. We take only image encoder because we have image input and image outputs of generator. We take image encoder, and I propose it use instead of Siamese network. That is our proposal. In result, we need not choose no architecture, no training parameters, because we use frozen weights from image encoder, no dimensionality. We only have to choose lambda coefficient between adversarial and travel losses. It is much more simple, and we can find optimal parameters. Let's back for our problem setting. What is semantically robust image translation? Images from GTA have more open sky, but European images have more buildings, trees, but a little area of open sky. It's big difference. When we try to translate, most of previous models try to put something instead of open sky. They translate lane line correctly white instead of yellow lane line in American roads. It is white lane line. They translate cars, road, they hallucinate trees, buildings, everything, because discriminator can easily distinguish real images without big sky arrows, with fake images translated from GTA. What is semantic robustness? First row, it's original image and its label. That some models in third row translate with something, trees, buildings, everything instead of sky. But there are some models, some new models, for example, VCA, vector symbolic architecture, that translates absolutely correctly. Translation is semantically robust. They does not flip sky into buildings or trees. Let's try our model. We took a GTA 5 image and translated it with original travel gen. Original travel gen cars where there were no cars in original image, and some buildings and Mercedes hood ornament. It is not correct. We tried our model clip travel gen, where clip was instead of Siamese network. It was much more correct, but some artifacts instead of sky we could find. We changed lambda coefficient. We increased lambda, and translation was absolutely correct. And no artifacts. It was good enough. Another image. Again, travel again hallucinates trees, two Mercedes hood ornaments. Our model on low lambda hallucinates the same. We increase lambda, and translation is almost perfect. If you ask, maybe travel again, increase lambda there, and it will be perfect too? No. When we try together to learn Siamese network, generator and discriminator, and all parameters to be changed together, Siamese and increase lambda, it can't learn anything from image encoder, clip image encoder knowledge that were pre-trained on billions of image already can help to semantic to take semantic from images and compare them. It was very important that clip has same semantic knowledge of images as a human can describe the image. by language. Let's compare with state-of-the-art vector symbolic architecture. In upper row, we have translation of some image made by the best translation model, VSA. And second row, our model clip travel GAN. We can see that both translations are the same. So our model works near state-of-the-art VSA. But our model has limitations. When we choose problem that labels should be translated to European image, our clip can't help. Clip network was not trained on labels. It can't understand labels, so it can't help to correctly translate into image. Other architectures may do it much better.
Sorry, we have a few minutes for your report.
Okay, so summary our clip travel GAN. We propose to change Siamese network of clip travel GAN with clip with pre-trained weights. We were first to utilize clip to ensure semantical robustness of image-to-image translation. Clip was used in other image translation models, but to ensure semantical robustness of translation, we were first. Our method is simple, and it is a step towards semantically robust image-to-image translation. Our code is available for experiments at Schedule. We made it open. Thanks for your attention. Questions?
Thank you very much. Maybe some participants have questions to reporter. Not have. Maybe I have one question. Is it useful for real-time processing images?
No.
No.
No, it is very very slow model, of course, as any image-to-image models. They train very slow and can't be trained online. They trained on TPU on Schedule. We use TPU, not even GPU.
But you can train frame by frame in not in real time, but for some motions. Frame by frame translation.
I don't think that time consuming
Okay.
will allow it. I'm not sure.
Generally, your task was to do deep fake more reliable.
No,
No?
maybe yes, but it is not about deep fake realistic. It is about that semantic for one image will be shown in output image. But yes, it could be used for that too. But not for realistic, for more realistic, but for more semantically correctness.
Okay. Maybe somebody else has questions. No. Then thank you very much for your report. It's very interesting. Unshare your screen. Yes, thank you. And let I introduce next report, comparison of object detection algorithms for the task of detecting possible road accident. Who will?
Yeah.
Okay.
Yeah. This is Alexander Biskrony, and I would like to present you this article.
Please,
Yeah,
you have a screen.
So I'm sharing my screen. Yeah. Do you see it?
Yes. Okay, very good.
All right. So today I would like to present you the presentation or slides for article where the comparison of object detection algorithm for task of detecting possible road accidents is studied. Okay, let's move further. So the relevance of this work, like the road accidents, is a major problem today because of number of cars is increasing and their speed is increasing, and the number of victims and injured as a result of road accidents increases too. So, and modern methods of preventing dangerous situations on roads are focused on safety of each individual cars. And these systems do not consider the other road users who are beyond of richness of building mechanism for ensuring the safety of the car. And the reason is to create some methods for notifying the driver of dangers that may be detected in traffic areas or near traffic areas that cannot be scanned by existing ADS system due to impossibility of analyzing the traffic and different is beyond on the obstacles of various kinds. And based on the above, the development and research of new methods for monitoring driver behavior, predicting dangerous situation while driving, and notifying the driver about them is a popular and relevant task, and we need to pay attention for it. Yeah, and the aim or goal of this article or this research is estimation or identifying the algorithm which has the smallest time for prediction, smallest size, and good accuracy for current problem. Yeah, and also this problem based on the raw video stream, and we need to work with video. So this is kind of real-time detection. Yeah, and the data description, which is used for model training. So I would like to show you what kind of possible road accidents is taken into account in my article. So this is the turning left across oncoming lines, and when oncoming lines consist of few lines, and one line is empty and other lines contain stopped vehicles to skip the driver which would like to turn left. So this is kind of not by rules or road rules, but this is for ethics between drivers. So it could be possible on the road. And the red anchor show here the possible trajectory of car which going on oncoming line. And this car possible cannot see the car which is turning left. Yeah. And the current problem requires to use the raw data, where raw data is a video stream from danger places. And danger places here, this is a crossroads and maybe crosswalks. And I have used the BMNG Drive game for forming the video stream and also the data set for training and validation. I captured near 500 images just to verify whether my problem can be resolved or can be resolved with the following algorithms. Yeah, the algorithm I will present further. And the metric which I have used to validate which one model is better, the average precision with union time to train, occupied GPU memory for training, and also for detection, model size, loss classification, loss box, and inference time metric. Yeah. So, and I went through the list of the most not comparable, but the top ranked algorithm for object detection and training, and found there the YOLO family and Detectron family. And YOLO is a great algorithm which is used for real-time processing. And the key feature of YOLO is ability to detect objects in a different scale. So YOLO can be used with the images, different size of pictures present. Yeah. And the YOLO models are designed to detect objects in real time by single pass. Yeah. And this makes this family of algorithm very efficient for application where speed is critical. And for our case, this is also applicable because we need very fast processing just to notify the driver about possible road accidents. And as opposite, the Detectron 2 was used. This is open source object detection framework by Facebook, and it is built on top of PyTorch. And this framework contains already pre-trained models. The faster RCNN, RetinaNet, and Mask RCNN. And in this article, the faster RCNN was used. Okay, let's move on. And this is the results comparison. This slide about training. And for YOLO V7, we use batch size 16, image size for both algorithms the same, 640 pixels, but epoch count was different. But this epoch count provides nearly the same accuracy of both models. And as you can see, the Detectron 2 takes much more time for training. This is near the 1 hour. But for YOLO V7, we have 16 minutes. That's great. And the training environment, which training was Google Colab. And also the GPU Tesla T4. Yeah, and I'd like to add that YOLO V7 use more GPU memory for training. So this is 11 gigabytes in comparison to Detectron, which have 8. Okay, and this is results after evaluation of model YOLO V7. And for metric average precision with intersection over union 95%, this is near the 60 percentage of precision. This is quite low, but I guess we need to increase the number of images in the will increase possibly. But for the average precision with IOU 50%, quite good precision, 90%. Yeah, and inference time, so it means detection time for each frame takes 0.90 seconds per GPU. Yeah, and model size for YOLO V7 is 74 megabytes which is okay. So let's proceed to inference result. And as you can see, YOLO with probability or precision 76% detects the danger situation, and also it is able to detect non-danger, where all lines stopped to skip the vehicle which would like to turn left. Great. Let's move on to the detectron. And detectron has higher average precision for average precision metric with intersection over union 95%, but lower for average precision with 50%. And also it has near the same inference time, but much more bigger model size. It near the 50, or not 50, sorry, 800 megabytes. Yeah, let's move on to the inference result. Yeah, and we found here that on the not slide, but result where the not danger, there is some not incorrectness, but slight mistake for detection in comparison to the YOLO algorithm. But danger situation found okay with 100%. So in conclusion, I'd like to say that this research is kind of background for further investigations of how to use such model, how to improve these models to use in the onboard computers, use such product, I guess, on the common road in the Ukraine, for example, on the, or maybe in UK or USA, but for all of the mentioned countries, we need to have own data set, trained data set with own images for the road traffic. Yeah, and this research was the data set for training of this model was grabbed in the BMNG drive, which I guess has a difference with real traffic in the countries. So yeah, and based on the evaluation results, it has slightly better results and better performance than Spectrum 2, and it will be used for further investigations, how to integrate into onboard computers and how to improve the model to have better prediction, better accuracy, etc. Thank you for your attention. Maybe you have some questions, you please ask me.
Thank you very much, dear Alexander. Somebody has questions to reporter? No. Maybe I ask you how to I can use your project or it is only a starting point for such software to be used anywhere?
Yeah, this is a starting point to understand whether we can use such models for prediction or not. And in general, this is kind of a small part of a whole ecosystem. The general idea was like this onboard computer will identify the possible road accidents, and after that the notifications will go to the driver, which is going on the line under which is assumed like this is danger line, and this was the idea. Yeah, and the current research cannot be used separately without these notifications, because this is useless maybe, or it could be used for grabbing some statistics, which one road crossing in the city is most dangerous without low. My battery is running off low, sorry. Yeah,
very good. It's enough for your battery for your report. Yeah, thank you very much.
Yeah. Thank you.
Any other questions? No other questions. Thank you. Thank you, Alexander.
Thank you.
And the next report, CNUNet, robust network based on deep convolution for medical image segmentation. Who will make this report?
Can you hear my committee?
Yes, very good. Okay. Let me say that we should state regulations no more than 10 minutes for report and 5 minutes for questions. Okay?
Okay.
Okay, thank you. Please.
Thank you. Good afternoon, ladies and gentlemen. It's a great honor to be part of this meeting. Today I will share my paper here. The title of my paper is CNUNet, a robust network based on deep convolution for medical image segmentation. I will introduce this paper in 4 sessions, namely introductions, methods, experiments, and conclusions. First, we need to know that the field of study in this paper is medical image segmentation. Medical image segmentation is an important research direction in the field of medical image segmentation, and some important progress has been made. Common medical image segmentation tasks include tumor segmentation, liver segmentation, and multi-organ segmentation, and so on. Medical image segmentation methods based on deep learning can be roughly divided into 2 types. One method is based on convolution neural network. Commonly used ones include ULET, ULET plus, and so on. The other type is based on transformer, which includes newly proposed networks such as trans-ULET, swing-ULET. And Convex is a convolutional neural network-based semantic segmentation model. Following the idea of swing transformer, Liu designed a convolutional neural network and demonstrated through extensive experiments that convolutional neural networks are not inferior to transformer-based networks, and in some aspects even superior. However, Convex still has some issues in image segmentation tasks, such as in insufficient utilization of contextual information, poor segmentation performance, satisfactory processing of imbalanced data sets. Inspired by the Convex network, we propose a deep convolutional 2D medical image segmentation structure called CNUNet. CNUNet is based on the U-shaped symmetric architecture constructed based on deep convolution with the same block as its basic units. To fully exploit the powerful feature extraction capability of the CN block, we divided both the encoder and decoder of CNULET into 4 stages, with the CN block proportions of 3, 3, 3 in several stages. Skip connections were added between each corresponding stage to restore the contextual information of the feature maps. The main structure of CN block is shown in the figure. It is a pure convolutional module obtained on the basis of restlet block by borrowing the advantages of swing transformer block. Each CN block consists of inverted bottleneck, layer normalization, and G-loop. In order to obtain a larger receptive field, the CN block has the ability to more approximate the global receptive field. In the selection of the convolutional color size, CN block uses 7 convolutional color. In order to avoid the lack of data to affect the efficiency of the model, a multiple data enhancement module dedicated to medical data is proposed. The module is divided into 3 branches. And the first branch is DA gain data augmentation. Before the images were input to CNULET, the labels of samples were randomly selected and subsequently entered into DA GAN network for semantic generation. Additional generated image can be obtained through the DAGN network. And the other 2 branches are slice fusion augmentation and test time channel grayscale slices, 3-channel RGB image, effectively preserving the context of the data. Of course, it is also possible to directly convert a single channel slice into a 3-channel picture, but this only simply copies the information of a single slice, which not only doesn't capture the information between adjacent slices, but also causes the data redundancy. To further reduce the generalization error during training, test time data augmentation is introduced in the multiple data augmentation module. To verify the effectiveness of CNULET, we conduct experiments on 2 common used datasets, CLEFs and ACDC datasets. We chose to compare with the current and the transformer-based architectures, using the reported results to explore the research in the field of medical image segmentation and demonstrate the superiority of CNULET. This is a correlation of the results of different methods. The results of comparative experiments are shown in the table. We can see from the table that our method obtains the highest scores in four semantic classes, this, and this. And it also get the highest average death score. Next, we conducted ablation experiments on MDA module, and as shown in the table, each branch of this module had a considerable effect on the backbone network, and our designed network structure also coverage the faster than convexed. And this is a visual of the results. In this paper, we proposed a 2D medical segmentation network, CNULET. CNULET is a robust deep convolutional network. We designed it as a U-shaped symmetrical structure, and the basic design is the same as CNULET. Experiments on CLabs and ACDC datasets show that our CNULET achieves promising results on 2D medical segmentation, which shows it has good segmentation performance. The above is the whole content of my report. And thank you guys for listening.
Thank you very much.
Thank you.
Maybe somebody has questions to reporter.
Yes, I have a question.
Please.
Is your model publicly available for experiments?
Pardon?
You understand?
Is code of your model publicly available for experiments?
Is it model is somewhere in internet to download? No?
Internet.
Yeah, accessible. This package, software package is available online.
We can put this on internet. Yeah.
Okay, it will be interesting. Okay.
Yeah, we can put it on it.
To compare to other models, maybe.
To use, I use UNet, usual UNet, so I could try CN UNet in my image-to-image translation model, if it is available on GitHub somewhere.
Yeah, we can, but I think our changes are not good enough, but our results are pretty good. So I think is not really good methods.
Thank you.
Okay, thank you. Other questions? Maybe somebody has no question. Thank you very much, reporter. And
Thank you,
we
Tommy.
can go to next report. Yeah, thanks. Report is research on traffic flow prediction based on ISMA CNN GRU model. Who will be reporter? Hein Hu Jian. Okay. Yes, screen sharing not started. Repeat, please.
And also we are not hearing you.
I started screen sharing. That are present this Hui Jian. Please replay. No. Okay, then maybe next time, and we will go to the followed reporter. Can you unshare your screen, please? Tian, Dr. Tian. Yeah, okay. Then if is problem with Dr. Tian, Maybe you will try again once more. Share your screen. No. I see that is problem we share. Okay, let it will be maybe next time, and we will pass your, please. It's some problem with connection, maybe. Internet connection. Let we try it next time, but this time, please, next reporter. Rudenko, Bessonov, Shaina, Piskunov, CNN Basic Predictive Maintenance of Generalized Rotational Equipment. And Dr. Tian will try after coffee break, maybe. Please unshare your screen and let's try next reporter. Who is present from next reporter? Oleg Rudenko, Alexander Bessonov, Andrei Shaina, Stanislav Piskunov. No one? I cannot see. Okay. Then, once again, Dr. Tian. If it is possible. If not, then we will go into coffee break. Dr. Yanov absent. Rudenko, Bessonov, Dr. Rudenko or Bessonov. No. Okay, then we shall go to coffee break until 2:30. Thank you. Coffee break.
Thank you.